Hello everyone, thanks for watching our video. I'm Tian Xinyu from Northwestern Polytechnic University. The title of our paper is A General Divergence Modeling Strategy for Salient Object Detection. First, I will introduce the motivation of our paper, starting from the task definition. Salient object detection aims to identify regions that attract human attention in an image. It can also be viewed as a binary segmentation task and is closely related to many tasks. In the process of silencing map labeling, the labeling is often done by multiple annotators, and then the regions that receive consensus are labeled as silencing after majority voting. However, most of the existing SOD models intend to achieve the point estimation from input image to the corresponding ground truth silencing map, neglecting the less consistent silencing regions discarded while generating the ground truth map via majority voting. In this paper, we study divergence modeling for SOD, representing the subjective nature of silencing. Our main contributions are: firstly, we introduce the first random sampling-based divergence modeling strategy for silent object detection to produce reliable object-level uncertainty map, explaining human visual attention. Secondly, we present an ensemble-based framework and three latent variable model-based solutions to validate our divergence modeling strategy. Thirdly, to maintain the deterministic performance, we also design an efficient majority voting branch to generate majority voting silencing maps without sampling at test time. Next, I will introduce our methods. Since we have limited samples containing diverse annotations, and training directly with all the annotations will generate a biased model, where samples with consistent annotations will dominate the training process, leading to less effective divergence modeling. We propose a random sampling-based strategy to randomly select annotations for model updating and apply it to an ensemble-based framework and three latent variable-based networks to achieve diverse predictions and effective silencing divergence modeling. For the ensemble framework, corresponding to M+1 silencing annotations, we design an ensemble structure with M+1 decoders of the same structure. Then, we randomly select a decoder branch and define its loss function as the final loss function for model updating. For the latent variable model-based networks, the encoder is same as the ensemble framework, but the decoder is combined with latent variable to obtain the final prediction. Our latent variable model-based networks include two main parts, namely a deterministic prediction network supervised by ground truth after majority voting, and a latent variable model supervised by randomly selected silencing annotations to infer the latent variable. Here, we have conducted experiments on three classic generative models, CAVE, GAN, and APP, to validate our strategy. For details, please refer to our paper. At testing time, since we set up a deterministic prediction head, we only need one forward pass to obtain the silencing prediction. For the ensemble framework, the uncertainty map is defined as the entropy of the multi-head average prediction, and for the latent variable model, the uncertainty map is defined as the mean entropy of the multiple predictions by changing the latent variable. Next, I will introduce the experimental results. We use the CAM dataset for training, as it's the only large silencing training dataset containing multiple annotations for each image. Here we also show some implementation details. As a divergence modeling strategy, we aim to produce both accurate deterministic predictions and reliable uncertainty. We designed the following experiments to explain the divergence modeling ability of our proposed strategy. Firstly, we train our model with all the annotations and report their performance as name with A in the table, and change the learning strategy by randomly selecting annotations to update model, and the results are shown as name with R in the table. The better performance of training with randomly selected annotations compared with training with all the annotations simultaneously illustrates the effectiveness of our strategy. Existing generative model-based saliency detection models are based on single ground truth to compare uncertainty maps based on the single annotation and multiple annotations. We train the 3 latent variable models with single majority voting ground truth and show the model performance in Table 3 and the visualization results in Figure 3. Different from our strategy with uniform uncertainty activation within the less confident region. The majority voting ground truth-based model usually generates uncertainty distributing along object boundaries, making it less effective in modeling the subjective nature of saliency, which explains the necessity of multiple annotations for saliency divergence modeling. We further analyze the uncertainty estimation techniques with less annotations and show model performance in Table 4, where we train our model with 3 different annotations. Compared with using 5 different annotations, we observe similar deterministic performance when using 3 annotations. Then, we visualize the produced uncertainty maps in Figure 4, which show that better latent space exploration can be achieved with more diverse annotations. To quantitatively analyze the effectiveness of uncertainty maps with the proposed strategy, we compute mean absolute error of the estimated predictive uncertainty and the uncertainty of the corresponding multiple annotations, and show the performance in Table 2, which show that our random sampling-based strategy leads to lower uncertainty-based mean absolute error compared with other strategies. We also compare performance of our baseline model with state-of-the-art SOD models and show model performance in Table 5. Our model shows comparable performance compared with state-of-the-art SOD models, while generating more reliable uncertainty maps, which is more informative in explaining human visual system. Further, we apply our strategy to one state-of-the-art SOD model, namely PSFNet, and show the deterministic performance in Table 6 and the uncertainty maps in Figure 5, which show that the proposed divergence modeling strategy can keep the deterministic performance unchanged and observe more reliable object-level uncertainty maps. To summarize, as a one-to-many mapping task, we argue that Salient object detection deserves better exploration with effective divergence modeling strategies. Our proposed divergence modeling strategy aims to explore those discarded Salient regions for better human vision system understanding. To achieve this, we proposed a general random sampling-based strategy and apply it to an ensemble-based framework and 3 latent variable models. Our extensive experimental results show the necessity of multiple annotations and the effectiveness of our random sampling strategy in modeling saliency divergence. Note that our saliency divergence modeling approach relies on multiple annotations, which can lead to expensive labeling costs. We will further explore flexation data from multiple observers to achieve both cheaper annotation and more reliable saliency divergence supervision. That's all my introduction. If you have any question, you can leave a message, and you are also welcome to communicate with us during the conference. Thanks for your watching.